Hi guys, we are going to skip the last section 1.7 in this chapter. So this section 1.6 is going to be the last one that we're going to cover in chapter 1, and it's focused on two-dimensional figures. And the good news is it's pretty much review from things that you've seen quite a bit in your past. So the first thing we're going to do is talk about polygons and how to classify them either by the number of sides, whether they're convex or concave, that type of thing, whether they're regular or irregular. And then we're going to just look at things that you know very well already: perimeter, circumference, and area of two-dimensional figures. Okay, so let's first talk about a polygon. First of all, a polygon has, we could say, n number of sides. And that is true as long as n is greater or equal to 3. So a polygon, a minimum, is a three-sided shape, and that would be, of course, called a triangle. We wouldn't be able to close up with just two sides, so we do need at least 3. And when I say sides, I really mean segments. So you could see over here that a polygon is not a circle. It doesn't have any arcs or rounded edges of any kind. So over here in the diagram, this polygon happens to be 1, 2, 3, 4, 5, 6 sides. We'll talk about what we call that in a minute, but you can see all 6 sides are made out of segments. They are straight. And each segment, we should say, is coplanar. So therefore, it is a polygon is flat. So you should write that down. Each segment is coplanar on the same plane, same flat surface. Okay, moving on to other vocab. The vertex of a polygon. The vertex of a polygon, shown here in the diagram, are these points. I'm actually going to make them noticeable. So J is being located there. I'm going to draw all the points. These, a vertex of a polygon, that's singular, and the plural is vertices. And those are basically common endpoints between each of these segments that are making up the polygon. So that's what vertex or vertices are of the polygon. Okay, and if we wanted to talk about naming the polygon, I didn't put a spot here, but name the polygon. We can name it in a variety of ways. And we're going to use all of the vertice labels of each polygon to name it. Now, I don't have to go in order of the alphabet, in other words, starting with G. I don't have to do that. I could start with any one of these, really, but I have to kind of be organized about how I would name it. I have to either go clockwise, that's clockwise, or counterclockwise. Okay, those are abbreviations. And you have to be organized about it. So you can't start with, say, H, and then cut over to L, and then cut over to G. You have to start with one, doesn't matter which one, but you have to go in a clockwise fashion or a counterclockwise fashion. So if I wanted to, I could say this is G, polygon G, H, J, K, L, M, and I've gone in a clockwise manner there. Okay, now let's talk about classifying polygons. We have different ways to classify them. We classify them by whether they are concave or convex. We classify them by the numbers of sides or segments that they have. We classify them by whether they are equilateral, equiangular, or regular. So let's talk about each one of those in order. So first of all, concave or convex. That's kind of trying to decide, is this polygon have any kind of cutouts in them or not? So what I like to think of is this cave. Concave means it has a cave. Or maybe let's think of it as a cutout. And then convex would be that it doesn't. That would be the opposite. Okay, so we've got various polygons over here. They've all got straight segments made up of it. It is a closed figure, by the way. I should have said that above. A polygon has to be closed. And here, a reasonable way to test out whether or not it's convex or concave, if it's not obvious to you, you can draw segments over each of the sides. And if I do that on this arrow here, you can see that some of my segments are going into the shape itself. So if I draw lines, basically unending lines over each segment, and if any of those lines are going over the figure, then this has a cave. This would be concave. It has cutouts. Whereas here on this hexagon, if I draw an unending line over each of my segments, you could see that not a one of those lines are going over or inside the figure. So we would call that convex. Convex. And hopefully it isn't too difficult to see that this would also be convex without even me drawing the lines. And this thing here that maybe looks like a, I don't know, an old-fashioned cradle or something, this would be concave because it does have a cutout. This is a C, by the way. It looks like an E, but it is a C. All right, so concave, convex. Now let's talk about classifying polygons as equilateral, equiangular, or regular. So equilateral, that means that the lateral segments or the lateral edges are equal in length, or you could say they are all congruent. So here in this figure, we see that we do have one pair of equal angles and another pair of equal angles based on how those arcs are notated. But here, all the sides are being shown to be of equal length with these slash marks. So this would be equilateral. Oops, my pen's not working. Equilateral. And likewise, equiangular is talking about the angles. So equal angles or equiangular would mean that all of the angles are equal measure or congruent. So in this figure here, hopefully you see it's a rectangle. The opposite sides are shown to be equal. So this here being equal and this opposite pair of sides are equal. Not all four sides are equal, however. But all the angles are being shown to be right, or 90 degrees. So this would be a case where the figure is equiangular, but not equilateral. And finally, regular means both equilateral and equiangular. So I'm going to write that down. Equilateral and equiangular. So in this figure, it happens to be a pentagon, 5 sides. We're going to talk about that. And you can see in the figure all 5 angles have a single arc, so they're being shown to be congruent. All 5 sides have a single slash mark, so they're being shown to be equal measure or congruent. Therefore, both equilateral and equiangular, we would call that regular. So this would be a regular pentagon. Okay, and now let's talk about classifying polygons by the number of sides. As I have already previously mentioned, in order to have a closed figure, we would need a minimum of 3 sides, and of course we call that a triangle. And 4 sides, you may or may not remember, is called a quadrilateral. Quad stands for 4. And 5 sides, we just talked about that. Penti, the root word pent, is meaning 5, pentagon. And 6 is, and I also talked about that, is a hexagon. Now, when it comes to 7 sides, the textbook calls the 7-side figure heptagon. hept meaning 7. But I was taught growing up more the French word for 7 is septagon, so you may see that as well. And 8, the most popular regular 8-sided polygon, is a stop sign, and we call that an octagon. Usually people remember that from an octopus, 8 legs. 9 sides is called a nonagon. And a 10-sided figure, you might suspect, would be called a decagon, decade meaning 10 years. And an 11-sided figure is, in my opinion, hardly intuitive. It happens to be called a hendecagon. A 12-figure is a dodecagon. Both of those probably not something that you would be familiar with. And then finally, for just a placeholder or variable, we would call an n-sided polygon an n-gon. And it's not really necessary to memorize some of these. I would say you really should, though, know the names of 3-sided all the way up to, let's say, 8. So this part, I think it's pretty important that you know these. Probably less important that you particularly memorize that. All right, here comes the review part. Perimeter, circumference, and area. This should all look completely familiar to you. But if we have a triangle, say here, of 3 sides, this is a 3-sided polygon. The perimeter would just be the sum of the sides. And in this particular diagram, the side lengths are B, C, and D, so we could just simply write an expression, algebraic expression, B plus C plus D, and that would be the perimeter. And the area for any triangle is 1/2 base times height. 1/2 base times height. In this case, the base is going to be, well, let's start with the height. The height would mean you drop from one vertex perpendicularly. That means drop to the opposite side at a 90-degree angle, perpendicularly, and whatever that opposite side is, that would be the base. So the area would be 1/2 base times height. That should be somewhat intuitive to you because the base times height is the area of a rectangle, and we could always make a triangle half the area of a rectangle. So that should make some sense to you. Now let's talk about a square. A square has 4 sides of equal measure. They are all congruent, so we could actually show that all of these are congruent. And in my diagram here, the sides are S in length, and so we can add up all 4 of those, and we could say S plus S plus S plus S. And of course, repeated addition is multiplication, so we could say the perimeter is 4 times S. And the area would be S times S, or we could simplify that to be S squared. Okay, now let's look at a rectangle. A rectangle is also a quadrilateral, but all 4 sides are not congruent, but we do have 2 pairs of opposite sides that are congruent. So I'm going to mark it that way. Like a square, all of the angles interior to the polygon are 90 degrees, or right angles. And right here, if we have one side being L, then the opposite side is L, and one side is W for width, then the opposite side is width, and we could say that the perimeter is L plus W plus W, and we can simplify that to 2L plus 2W. Most people have seen that before. Now on the MCAS reference sheet, you'll actually see base and width in place of length. Base and height in place of length and width. And then for the area, getting the space inside or interior, we would just multiply the length times the width. And again, on the MCAS reference sheet, you would see the base times the height in place for the area. And the circle, we call the perimeter, if you will, the outside length of that circle. We have a special name for that, called the circumference. and the outside circumference is going to be 2 times pi times the radius. And pi is a constant, an irrational number that most people know is 3.14, and it goes on and on forever in a decimal format in a non-repeating way. We could also say then 2 times the radius happens to be the diameter. So we could also say the circumference is the diameter times pi. And the area is going to be the radius squared times pi, or you usually see that listed as pi r squared. And some students, it's really common to get these two mixed up, but the good news is both of those are on the reference sheet, so you'll always be able to discern either. I like to always remember that square units are always area, and so that's why I know that it's the pi r squared for area. All right, let's take a look at a couple of examples. Find the length and the width of a rectangle whose perimeter is 20 centimeters and whose length is 3 times its width. So always when I have a word problem like this, I always start with some kind of diagram. So here is a rectangle. I've got 90 degrees. I've got opposite sides being congruent. And we know that the width is something. We don't know what it is, so of course I'm always going to put a variable or placeholder, and I'm going to use W for width, and we're told that the length is 3 times the width. So if this is the length, I'm going to say the length is 3 times the width. Maybe I'll put a little equation there. Find the length and width, and now we know that the perimeter is adding up all the sides, and I've got 3W plus 3W plus W plus W, or I could have went to my formula. Perimeter is, and these are all like terms, so I've got 6W plus another 2W is 8W. And we're told the perimeter is 20, so I'm now going to substitute in. And I'm going to solve by isolating that variable. And I have W equals 20 over 8. I'm going to simplify that maybe to, let's say, 5 halves. I'm dividing both sides now by 4. And 5 halves, I guess I could put that as a decimal if I wanted to as well. That's 2 5/10. And I guess that would be centimeters. So we know our width is that, and we're asked for both dimensions. So the length is 3 times the width. The length is going to be 3. I guess it's, I don't know, it's just as easy to use the decimal as it is the fraction. The length then is going to turn out to be, well, let's use this as a learning experience. We're going to say 3, I'm going to use the distributive property. 2 5/10 is 2 5/10. Therefore, I have the length of 6 plus 1 1/2, and the length is 7 1/2 centimeters. So my polygon here, my rectangle is 2 1/2 by 7 1/2. I can go ahead and check my work and make sure that that leads to a perimeter of 20. So 7 1/2 and 7 1/2. Let's check. Let's do that check up here a minute as well. 7 1/2 and 7 1/2 would be 15. And 2 1/2 and 2 1/2 would be 5, and therefore my perimeter does indeed equal 20, so everything checks out. Okay, find the perimeter and area of this particular pentagon ABCD. It's on the coordinate plane, and it has locations for each of the vertices as listed. So the easiest thing to do here would be to first find the lengths of ED and DC. Since they're vertical and horizontal lines, all I need to do is count the units here. So ED is 1, 2, 3, 4, 5 units in length, and DC is 6 units in length. So that part is easy. Now I have to do a little bit of work to find the segment length EA, AB, and BC. So let's go ahead and imagine our right triangle here where EA is going to be the hypotenuse. So I have 1, 2, 3 units here and 3 units here. So EA I'm going to put this over here. EA is going to basically be C. C squared equals A squared plus B squared. So EA squared is going to be 3 squared plus 3 squared. EA squared is going to equal 9 plus 9. EA squared is going to equal 18. And I'm going to take the inverse operation of squaring, which is square root, and I get EA is going to equal the square root of 18. And at this point, maybe I'm going to use my calculator because I know I've got to find the perimeter, which means I have to add up all the sides. So to add a number, an irrational number like the square root of 18 to numbers like 5 and 6, it's probably easier for me to go ahead and round that number to some decimal. And I'm using my calculator, and I get 4 24/100 units. So that would be the length of EA. And we're going to do the same thing with AB. We're going to imagine this right triangle over here. One side is 4, the other side is also 4. So I have AB squared, or C squared, equals A squared plus B squared. That's our Pythagorean theorem. So this hypotenuse C here is going to, its square is going to be 4 squared plus 4 squared. AB squared equals 16 plus 16. AB squared equals 32. And again, the inverse operation is square rooting. So AB equals the square root of 32. And if I again use my calculator and just round, I get the square root of 32 is approximately, I really should use approximately here, is approximately 5 66/100 units. And finally, and I'm going to do this last one rather quickly in the interest of time, we've got a right triangle over here of 1 side and 4 side. So CB squared is going to equal 1 squared plus 4 squared. CB squared is going to equal 17, and therefore CB is going to equal the square root of 17, which is approximately 4 12/100. So bringing it all together then, the perimeter is going to equal 5 plus 6 plus 4 24/100 plus 5 66/100 and plus 4 12/100. If I put that all together, I get a perimeter of approximately 25 200 units if I did everything correctly. So that would be my perimeter. Now how can we get the area of this irregular pentagon? It is not a regular pentagon. We've got various different angles. Well, you can cut this, let's call it a compound area, into things that you know, such as triangles, rectangles, and squares. That's the easiest thing we can do. So I'm going to just, and there are many ways to do this, but I'm going to look at this rectangle here as an area. And I'm going to look at this triangle up here. I'm going to call this triangle area sub 1. I'm going to call this rectangle here area sub 2. And then I have a little triangle over here, area sub 3. So I know if all of these areas do not overlap, then I can sum each of those areas to equal the compound area, which is this irregular pentagon. Okay, so if I look at that, I'm going to have to carve out some space over here. Area 1. Area 1 is a triangle, so we know that's 1/2 base times height. Area 1 equals 1/2. Well, the wonderful thing about the coordinate plane is it's got these perpendicular lines. So it's very nice to call this here this height of 3 units. And the base then is the side opposite it is 6 units. So I've basically got 1/2 of 18, which is 9 square units. So that's area 1. Area 2 is a rectangle, which is length times width or base times height, whichever you like to look at it. And I've got 1, 2, 3, 6 as a base, and the height is 5. So area 2 is 30 square units. And area 3 is a little skinny triangle. And here's where you want to look to see where are the perpendicular segments here. I'm going to call this little piece right here the height, because that is perpendicular to this vertical piece, which is the base. So in this case, the height is not really up and down, if you will. It's kind of left and right. But what you're looking for is the base and height to be perpendicular. So I'm going to call that base, well, first of all, 1/2 base times height. I'm going to call that base 1, or sorry, the height 1. Then that would make the base 1, 2, 3, 4, 5. And so we end up with an area 3 of 1/2 of 5, which is 2.5 square units. So if I add all of these up, then the area total, I'm going to call that area sub t, then I have 39 plus 2.5, which would be 41 and 5/10 square units. And that would be our area. Okay, finally, last problem. Find the circumference and area of the circle below. In this case, the circle is on the coordinate plane. So this is a little tricky. We need to find what the radius is. And of course, the easiest thing to do is look horizontally or look vertically. And what do you notice? Problem here is that the outside of the circle is not going right through the grid. So I would have to estimate how much that's over, and that's always going to create error. So what you really want to do is look at areas where the circle is going right through the grid, and it's going through there. You can see it's also going through here. All of these radiuses would be of equal measure where it's going through the grid. So here I'm going to look at this as a right triangle, and I want to find that hypotenuse, which is going to be our radius. And over here, one side of the triangle is 1 unit, and the other side of the triangle is 2 units. So c squared